So this unit is about thermodynamics, but in order to actually get started, we're going to review what we've already talked about regarding thermochemistry, which we studied in a previous unit. And so the first thing we need to talk about is this first law of thermodynamics, which we actually already talked about. And the first law of thermodynamics states that energy is going to be conserved. And the other thing that we talked about is that if a reaction is endothermic, what that means is that its enthalpy change, its delta H, is going to be positive, while if it's exothermic, its enthalpy change is going to be negative. All right? And so what I want you to do right now, I have some thermochemistry review for you here, and I want you to pause this video right now and complete that, and then we'll go over that in class next class period. All right, so the key thing for you to know, a big misconception, is the thought that thermodynamics tells us how fast a reaction occurs. That's actually not the case. Thermodynamics only tells us the direction that the reaction goes and the extent to which the reaction proceeds, but it does not tell us how fast the reaction goes. That actually is kinetics, which was, I believe, 3 units ago. So when we're talking about thermodynamics, we're not talking about how fast a reaction is. Instead, we're talking about the direction that the reaction proceeds and to what degree it proceeds. Okay, so we're going to be talking right now about a spontaneous process. What exactly does it mean for a reaction to be spontaneous or any other process to be spontaneous? And so a spontaneous process is one that proceeds on its own without any outside assistance. So a great example is the rusting of a nail. When a nail rusts, it doesn't actually require any outside help at all for that to occur, and therefore it's going to be considered a spontaneous process. Now the interesting thing is that if you have a spontaneous process, it's only going to occur in one direction. So for example, when a nail rusts in that one direction where iron and oxygen are reacting to create iron oxide, that is a spontaneous process. Now the opposite reaction, so the reverse reaction in which iron oxide will become iron and oxygen, that which is the reverse process, it is non-spontaneous. So in one direction a reaction is spontaneous. If you look at the reverse reaction, it's going to be non-spontaneous. All right, so another important thing for you to know about spontaneous processes is that they depend on temperature. So if we look at water, if your temperature is above 0 degrees Celsius, what that tells me is that I wouldn't have to put in anything in order for water to melt, right? And so therefore melting at a temperature above 0, melting is going to be spontaneous. Now freezing, you would have to put it into a freezer or remove energy in order for freezing to occur, therefore freezing is non-spontaneous. Now if for water the temperature is less than 0, that means that freezing is spontaneous while melting is non-spontaneous. And now the interesting thing is at 0 degrees Celsius, you're actually in equilibrium, meaning that the rate at which freezing occurs equals the rate at which melting occurs. And so whether or not a reaction or a process is spontaneous also depends on temperature. So that's something important to keep in mind. Now the next concept, we've already very briefly touched on this concept, but when we talk about a process being spontaneous, one of the assumptions we had made before is that the majority of spontaneous reactions are exothermic, and that is actually the case. That is true. However, that is not always the case. There are some endothermic reactions that are spontaneous, and so in order to understand that, we need to talk about the concept of entropy. Now, entropy is a measure of the disorder in a system, and we'd already brushed on entropy just a little bit. And so that brings us to the second law of thermodynamics, which states that any spontaneous change is going to be accompanied by an increase in entropy. So if entropy increases, that means that the reaction or the process is going to be spontaneous. And so just a couple of situations in which we expect entropy to increase include a gas forming from a solid or a liquid. And now remember, entropy is a measure of the disorder. So if you're creating a gas from a solid or a liquid, in a solid or a liquid, the molecules are much more confined. They're restricted movement-wise, and therefore when you're producing a gas, they're much more free and there's much more disorder. If you form a liquid or a solution from a solid, again, you're creating more potential for disorder, and therefore the entropy is going to increase. And the last one is if you increase the number of gas molecules in a chemical reaction. Again, gas molecules are much more free to move around, they can occupy a larger volume, and therefore there's going to be more disorder. So as you can see here, as I move from ice to liquid water to water vapor, the entropy increases simply because the ability of those molecules to move and their freedom results in more disorder. The other concept, which was a solid being dissolved into a liquid, it's interesting because you've got two different situations that are occurring. First, you're taking the solid and you're allowing it to dissociate. Now, that dissociation increases entropy. But the other thing that you're doing is you're forcing water molecules, which were free to move around, to then bind to those ions. So water's entropy decreases while the solid's entropy increases. Now, when you end up balancing it out, it turns out when you do dissolve a solid in a liquid, ultimately the entropy increases despite the fact that the entropy of the water of the solvent decreases. Okay, so the last concept that we're going to go over is the third law of thermodynamics. And in the third law of thermodynamics, it states that the entropy of a pure crystalline substance at absolute zero is actually going to be zero. And so what that allows us to do is to have a reference point to compare entropy changes when we have a chemical reaction. So if you look at this graph that we have right here, entropy is your y-axis and temperature is your x-axis. So as your temperature increases as expected, your entropy would increase simply because the molecules are better able to move around, they have more freedom and therefore more disorder. When you see melting and boiling, you see those huge jumps in entropy. They're vertical jumps simply because when you move from a solid to a liquid and from a liquid to a gas, you have even more freedom for those molecules and therefore the entropy is going to increase even more. Notice for boiling that the entropy increases to a larger degree than when melting occurs. So this formula right here should look extremely similar because we use this when we're talking about enthalpies of formation, but instead what we're going to be using this for, the S represents entropy, entropy of your products minus the entropy of your reactants. And so a couple of rules include the fact that the standard molar entropy for elements at 298, unlike enthalpies which were zero, for entropy, they are not zero. The other rule is that the standard molar entropies of gases are going to be greater than those for liquids and solids, which is what we expected based on our previous discussion. The standard molar entropies are going to increase with increasing molar mass because the larger your molecule, the greater ability or the greater ease there is to have disorder. And then finally, as you increase the number of atoms, again, your entropy is going to increase. So we're going to look at this example problem right here. And so you're going to calculate your standard entropy change. And so we have this reaction. And so I'm going to use this formula. And so I know I'm going to look up on the appendix the entropy, the standard entropy of aluminum, and it's 28.32, and I'm going to multiply that by its coefficient, which is 2, and I'm going to add to that 3 times the entropy, the standard molar entropy of water, which is 188.83. And from that, I'm going to subtract the standard molar entropies of my reactants. So for aluminum oxide, it's 51.0 plus the standard molar entropy of hydrogen gas times 3, since you have the coefficient 3, so that was 130. And so when I add those together and then subtract, I end up with 180.39 joules per Kelvin.